Good morning, my name is Francesco Di Cicco, and in this presentation I will discuss how flow curves can be measured using nanoindentation techniques. Before I begin, I will give a brief summary of the presentation. I will start by defining the goal of the topic. Then, I will explain the main differences between the two families of nanoindenters regarding the measurement of the flow curves. After this general introduction, I will go into more detail with two examples of studies that have used different approaches to obtain stress-strain curves from indentation testing. Indentation testing is relatively simple, small-scale, and it only needs a small amount of material, which is why it's widely studied to get stress-strain curves. In his early work, Tabor used cone-shaped indenters with different angles and found that hardness and representative stress are linearly related through a constant called constraint factor, which for metals in full plasticity is about 2.8. However, this factor isn't always constant. It increases with increased representative strain and the ratio between elastic modulus to stress. Instead, the representative strain depends on the indenter's opening angle and scale with the cotangent of that angle. Once the representative stress and strain are defined, determining the flow curves becomes straightforward. For a particular conical indenter, due to the geometrical self-similarity, the strain within the material is constant, independent of the load applied to the indenter. So, as shown in the image, using different tips with varying angles provides discrete stress-strain points, that is one data point for each indentation experiment. On the other hand, spherical indenters can generate a continuous stress-strain curve from a single indentation, because the strain field beneath the indenter evolves as the indentation depth increases. This allows obtaining the entire flow curve from just one test, since the local contact angle in spherical indentation effectively changes with depth. The image on the right shows hardest trace curves from the 3-indentation experiment using the same spherical tip radius. From this, stress-strain curves can be obtained by converting hardness to stress through the constraint factor. Now I will move on to the first example, where an nanoindentation approach using multiple sharp tips was applied to extract flow curves. The image on the right shows the materials tested, which are nickel and tungsten with different microstructures. Indentation tests were performed using the continuous stiffness measurement option. Hardness and Young modulus were determined following the standard Oliver and Farr method. Continuous stiffness measurement allows the mechanical properties to be measured continuously as a function of the indentation depth. For isotropic materials, a stable horizontal Young's modulus profile over displacement is a good indicator of reliable measurement, as shown in the image on the left. For sharp tips, the projected area is described by the first formula reported in the slide. Considering a perfect tip, the geometry constants b1 to bi become 0, and b0 depends on alpha, the phase angle. The terms after the lead term will mainly account for tip imperfections. By calibration of the area function on an isotropic material such as fused quartz, one can assess b0 experimentally and determine the actual phase angle. In order to calculate the representative strain of the respective tip, the variable indenter geometry is converted into an equivalent cone, and so the corresponding cone angle theta is calculated. Since the elastic modulus to stress ratio is high, the constraint factor can be considered constant. The continuous measurement of stiffness and the stable Young's modulus profiles confirm that pi-labs do not significantly affect the results. Once the constraint factor and representative strain are defined, the stress-strain curves can be obtained. As shown in the images on the right, the nanoindentation results for nickel and tungsten match very well with literature data from neaxial tests. Now I'll present the second example where spherical nanoindentation was used to extract flow curves. Tests were performed using continuous stiffness measurement and spherical tips with different radius. The study focuses on ultra-fine-grained and nanocrystalline materials where the indentation volume is representative even at shallow depths, so anisotropy and size effects are minimal. Fabricating spherical tips from hard anisotropic materials like diamond is challenging because small shape deviation can impact non-indentation results. 3D laser confocal scan and SEM images reported in the image reveal that tips are often ellipsoidal rather than perfectly spherical, so using a single radius is insufficient. A three-parameter function with constant adjusted with nonlinear least squares models the imperfect tip shape accurately. As can be seen in the images on the right, correct calibration and minor influence of pileup and sink-in are confirmed by horizontal profiles of the young models over displacement. In most modern high-performance metal, rate-dependent mechanisms are also responsible for high strain properties. Thus, controlling the strain rate in experiments is crucial to obtain useful flow curves. Strain rate control experiments were implemented based on the strain definition shown in the slide, by adjusting the proportional integral derivative control parameters. Once the strain rate is properly considered, spherical indentation experiments turn out to be extraordinarily stable and reliable, as it can be seen in the figure on the right, where the graph shows stable repeatability of 3 nanoindentation experiments. Assuming a constant constraint factor, it's possible to demonstrate the equivalence between the logarithmic hardness difference and the representative stress difference, which allows to extract the strain rate sensitivity. There are different approaches to determine strain rate sensitivity. One method is to perform multiple indents at constant strain rates. This method is time-consuming, but provides the strain rate sensitivity independence of strain. For example, tests on gallium arsenide wafer confirm that the parameter remains constant and matches reference Berkovich jump tests, as shown in the image on the right. Another method is to use jump tests. In this example, the figure on the right shows a hardness strain plot for an aluminum alloy, which exhibits pronounced strain rate sensitivity. The red dots indicate the strain rate during the tests, while the dashed red line shows the target strain rate levels, which are consistently achieved with only minor undershoots when slowing down. The analysis of the jump tests yielded a value that matches the Berkovich reference tests. The last step is the calculation of the stress-strain curves. The parameter mu directly relates to the plastic and elastic work and clearly distinguishes the elastic and plastic regime. Furthermore, it can be experimentally obtained from indentation if continuous stiffness measurement is used, by calculating the ratio of the contact stiffness and the slope of the load curve. Uniaxial tests were used to determine a function of mu for the constraint factor. This function was determined by matching the indentation flow curve to the uniaxial pillar flow curve of nanocrystalline nickel. As it can be seen in the graph on the right, the profile is divided in 4 regions and can be expressed as an empiric function. By this function, one can determine the constraint factor profile for each indenter, since mu can directly be evaluated from the nanoindentation device. Furthermore, for materials with similar work hardening behavior and frictional properties, the same function will be applicable, like our case. The figure in the present slide shows the comparison of 3 flow curves respectively obtained by pillar compression tests and spherical indentation experiments with variable and constant constraint factor, which clearly underestimate the yield level and not overestimate the work hardening of the materials. Obviously, the match in figure A is self-explanatory, since these curves were used to obtain the function. However, also the other graphs show excellent agreement, which make the assumption seems justified once materials with reasonably similar mechanical character are tested. To conclude, nanoindentation has proven to be an effective technique for extracting reliable flow curves. Using different types of indenters allows to tailor the data obtained. Conical indenters give discrete stress-strain points, while spherical indenters allow for the extraction of continuous stress-strain curve from a single test. Importantly, the use of continuous stiffness measurement combined with careful calibration ensures both accuracy and repeatability across measurements. Finally, the results from both sharp and spherical indenters align well with those from standard mechanical tests, which confirms the reliability of this approach. Overall, we can conclude that nanoindentation offers a powerful method for evaluation of stress-strain curves. Thank you very much for your attention.